Let's talk about number bases and number representations. The problem we're given is to convert from one base to another. So we could convert from base 10 to base 2, decimal to binary, or we could convert base 7 to base 13. And what we have to build up is our understanding of what a number base is, how numbers are represented, and then we can actually derive an implementation from that. So here we have base 10. Base 10 is what we normally use. It's basing our number system off the 10. We're going to see what that means in a bit, but we have the number 12 in decimal. We want to convert it to binary. The binary representation of 12 is 1100. Now, why is this the case? In order to understand why these numbers have the base they have and why their representation turns out to be like this, we need to look at what these number system representations really mean. So let's take, for example, 123 under decimal, under base 10. When we have the number 123, that is under base 10. We have a ones place, we have a tens place, we have a hundreds place, then a thousands, then a 10,000s, then 100,000s, then a millions, then a 10 millions, and so on. Those are our number places. This is what we learned when we were in grade school. And what this representation really means is we're living under a base. Our base is 10. So let me show you what that representation looks like. First, before that, let's establish our positions. What position is the 3 at? Let's index off 0. It's at position 0. What position is 2 at? It's at position 1. Because we're indexing off 0, it's in the tens place, but we index off 1. It's in position 1. And then that hundreds place. What position is that in? Position 2. And this is where the base kicks in. Each of these positions are the powers we apply to the base. And what the number represents is the weights of that individual power. When we have the 3, we say 3 times this weighting of 10 to the 0, which is just 1. We say 3 times 1. That says give me 3 10 to the 0s. 10 to the 0 is just 1. What does that now become? 3 times 1, just 3. So how much value did this position contribute to my overall integer, my overall representation? It contributed a value of 3 under base 10. And now, how much value does that contribute? 10 to the 1. We have 2 of those. Give me 2 10 to the 1s. All this representation says is, how do I modulate how many of these weightings of bases I take to my final value? So 2 10 to the 1s. Now 2 10 to the 1s is the same thing as 2 times 10. 2 times 10 is the same thing as 20. And I want you to notice we're going to add these representations up. 20 plus 3 is 23. That's what we have so far. And then this place, the hundreds place, says, give me 1 10 squared. Give me one of them. So we do 1 times 10 squared. And then 10 squared is just 100, so it's 1 times 100. So what this weighting, this place contributes to the overall sum is 100. And then 10 plus 20 plus 3 is 123. Okay, 123. So we got our original base 10 representation by breaking down our base 10 representation. Now, how do we convert other bases to base 10? We can use this exact same system to see what their actual value is in base 10. So let's take a base 4 number. What does that even mean? Let's get an example. Let's take the same exact number, except we're under base 4 now. And remember, our positions are the same, position 0, 1, and 2. Now we are summing up our work. The first position says 3 times 4 to the 0. How many 4 to the 0s do I want? I want 3. The number is just encoding based on what the base means. Number is just an encoding. So 3, 4 to the 0s. Ultimately, 3 times 4 to the 0s, same thing as 3 times 1, which is just 3. And then 2, 4 to the 1s. How much does that place contribute? It contributes 8 in value. So far we have 11 in value, and then 1 4 squared. And then we take the addition all of these. So what is 123 under base 4 as a decimal, base 10? Well, it's going to be the addition of all of these weightings contributed by our encoding, and that just becomes 27. And I think you get the picture. We could do the same thing for binary, base 2, same thing for base 7, same thing for base 16, which is hexadecimal, same thing for base 17, base 18, 19, 20, 21. How many bases can we have, though? Well, we have to consider how many representations we can possibly have. And let me quickly introduce to you hexadecimal. With hexadecimal base 16, there are 16 ways we can represent weightings within each digit of our encoding. So originally in under base 10, we had 10 ways to represent a digit. In hexadecimal, we can add 6 more ways. How do we do that? We add letters. By adding those letters, we added extra integers. We said 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. 0 to 15. 16 total unique representations. So when we ask ourselves how many unique number bases can we have as as bases as we have representations for a single digit. But in common terms, we only go as far as the alphabet. So we would go A, B, C, D, E, F, G, and then all the way down until we have 26 letters. Hexadecimal would stop at the F. We would have 16 unique representations from 0 to 15. The letters add on those extra ones after 10, 11, 12, 13, 14, 15. That's where hex stops. But we can go even farther by using the whole alphabet. 26 unique representations in the alphabet, 10 unique representations with raw numbers of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that adds up to 36 unique representations. That means we can have up to base 36 under this common system of using decimal numbers and then using letters. We can go even farther. As long as we can generate unique digits, we can continue generating bases, as long as we can represent them. As long as we can represent them, we can change whatever the weighting of the base we would like. And then this brings us to the overall question we have. We want to change base. We want to go from base 2 to base 7, from base 32 to base 5, from base 4 to base 12, from base 16 to base 22. How would we do that? Well, we just saw how we could go from any base to base 10. We would just use our weighting system, which is how numbers represent themselves, to convert to base 10. But how do we go from base 10 to any arbitrary base? Let's look deeper into that. In order to do this, we're going to use the example of base 4 with 1, 2, 3. This is under base 4, so this isn't 123. It's going to actually turn out to be 27. That's our target. So let's just keep that there just so we can notice some patterns. Instead of doing base 10, let's convert to base 16 instead as the final base. First off, we would take this base 4 number and bring it to base 10. So we're just going to create a for loop. We're going to loop over every digit. We know what place it's at. We know the base. We say, hey, 1 times the base to the place. And then that's going to be this weighting, and then we're going to see how much this guy weighs in, and then this guy weighs in. So we're going to do just what we did before. And this would just be an iteration with a for loop saying, we could start at the end and index off 0, I equals 0, and move this way, power our base, multiply it by the digit. Because we're getting this number as a string or an integer, either way we can get the digits we need to operate on. And then we would do what we did before, actually evaluate them. And now, 27 is the base 10 number. So we go into the second half of our process, which is going from base 10 to our final base, which is hexadecimal. Our hexadecimal representation is 1b. The 1 means 1. The b means 9 is 9, a is 10, 11 is b. So b means 11 in weighting. Now let's put the 27 up top and begin our second half of conversion, going from base 10 to base 16. Now that we have our base 10 representation, our target is base 16. We mod the base 10 representation by 16, which is our new base. And that's going to incrementally give us each digit out of this original value. So if we do mod 16 of this 27, we're going to get the first digit all the way to the right, which is 11. And our code's going to have to handle this value because we can't represent this with 0 to 9. And we know this is hexadecimal, so we can go above that. So we know that we can do 9, 10 is A, and then 11 is B. So this is B. It is the first term, and as you can see there, it agrees with our decoding. So we've gotten the B, and now we need to adjust the number. Now we adjust our number by dividing by 16. So 27 divided by 16 turns out to be this. And since we're storing this as an integer, we just truncate the decimal place. All we're left with is 1, and this becomes our new value at the new iteration of either our loop or recursion, and now we're going to mod this value. And now we will take the mod of this by 16, and the remainder, if we divide 1 by 16, is just the 1. We can't even do any division, so it's just 1. How do we translate this into anchoring encoding? Well, it's already between 0 and 9, so we don't need to go into the letters. And we can just say 1 goes into the next slot, and we see 1b. And now, again, we take the division. We divide 1 by 16, and we get 1/16. 0.0625, when we truncate the decimal, because this is an integer, we just get 0. And it's more obvious if we actually put the 0 there, truncate, and then we're just left with the 0. And then go back to the top of the recursion or loop, and we have nothing else to decompose out of the base 10 value into the new base, and we're just left with 0. Now, why do we do it like that? Here's the breakdown of what just happened. Initially, why do we use the mod operator to get that first value that goes in this first position? Well, we're going to do 27 divided by 16, which is going to be 1 because 16 goes into 27 one time, with a remainder of 11. That statement is the equivalent of saying 27 equals 1 times 16 plus 11. So you see how the lagging value, the leftover value in this division, is 11. That means we can express that first value as the first place, because 11 under base 16 is just b. And then what does division do? Division just gets rid of that remainder. When we divide 27 by 16, we get 1. We just get rid of the remainder, and we're left with this 1. And then we operate on the 1. When we operate on the 1, we ask ourselves, how can we express this in terms of base 16? And this brings us to the next slot. Then we're operating on this slot, the 16 to the 1. And we're saying 1 divided by 16 is 0, remainder 1. 16 goes into 1 0 times. We have a remainder of 1. And what we would actually do is we would do the mod operator. Why do we do the mod? Because the equivalent of the statement is saying 16 equals 0 times 16, 0 times 16 plus 1. We need to express that 1 because it can be expressed under base 16 as just a 1. And then we have a 0, so we can't express any more positions. So this is the equivalent reasoning of doing this as well. 27 divided by 16 is just 1 with a remainder of 11. And that means the 16 to the 1 place, its weight is going to be 1. And we still have to express the 11. So let's express 11. For the next position, we need to express 11 under the weighting of 16 to the 0. And that's just 1. And we can express that 11 with that weighting of 16 to the 0 with no remainder. And ultimately, that's what's really happening. We're expressing the original value, and then we say, okay, I expressed that. What's left over? I expressed the 11. And then 11 is expressed under this weighting, and then we have no remainder, so there's nothing else to express, and we've expressed the whole original number into the new number base using this new weighting system. So that's how you decompose back into this new number system from the base 10 that we converted the original base to. So now this is the final answer for our conversion, and this is converting number bases. I'll put more links in the description, and the code is in the description as well to look over how this is done concretely.